On the World Wide Web and on YouTube you can find many schematics, videos about the so-called Bedini circuits, about over unity. It means in general that you can get, the idea is, by the way, that you can get more energy out when you have a coil on its optimum resonance than you put in. Say you put 1 watt in, and when there is over unity and the resonance frequency is ideal, you can take 1.5 watt out, or perhaps even more. Of course, that cannot be true when we are talking about, say, the classical physical ideas of the conservation of energy. Anyway, I don't go too deep in that. My problem with all these circuits on YouTube and everywhere are that there's never a very precise, concise calculation, overview of the circuit, understanding of how that all works, say how the basic things of oscillation and energy transportation via coils work, etc., etc. So I've made a video a few days ago about that, 4 types of transformers, and now I want to demonstrate how you can find the optimum resonance of a transformer. Finding out the optimum resonance of a transformer. Well, I tested these 2 transformers, and the whole idea is very simple. You have here the transformer under test. The circuit is in a certain way the same as I published earlier, but now a few differences. We don't take the signal back from the high voltage side, so here is a disconnection, and have also removed the 500 ohm resistor. Be aware of the fact that when you do these experiments, the transistor combination, the Darlington, can immediately burn out when you go to a too high voltage, etc., etc., due to, say, voltage peaks that are, say, sent back to the, especially to the base of the first transistor. But because it's DC coupled, all these, say, damaging voltages will directly reach the base of the second transistor in the Darlington. But anyway, here again the pin connections. And these transformers were made for 50 Hertz in the Netherlands. This one worked best on 500 Hertz, and this one worked best on 300 Hertz, and you can test that in this setup by connecting a square wave oscillator directly to the base of the first transistor in the Darlington and send in different frequencies. When the frequency that is sent in matches with the optimal frequency here in the transformer, you know that you have found the optimum resonance frequency to make such a transformer work. And I'm doing that now, and I've used here an old school, very old school high voltage transistor out of an old school TV set with a cathode ray tube. When you know a little bit about the technology, it's old technology, but anyway, this is a high voltage coil, completely covered in a kind of epoxy resin, not epoxy by the way, special resin. And here is the primary winding, consisting of a few windings and also a back coupling winding, but I don't use that. I only use one of the primary windings, and there are on YouTube many videos where this is showed, especially with induction heaters. They work according to the same principle. But that's not the idea here. I want to show that this transformer has a certain resonance frequency, and it is around 16 kilohertz or 16,000 hertz. That had to do with the setup of all these old school cathode ray tube TV sets. This was responsible for driving the high voltage that make the CRT light up. Made for 16 kHz, let's see where the ideal frequency is. Connected my counter and my counter here. Now I'm on 1 kHz, and these are needle pulses, of course, and you can hear it beep. And this, of course, the gas-filled tube lights a little bit up. I've told in an earlier video that such a gas pillar inside such a tube also has a certain resistance, because there are ionized particles inside that tube that make the lamp, the tube light up. There's a fluorescent powder at the inner side here. The charged particle get to that powder and make that powder strays out light. So let's see, and that's also regarding all these Bedini circuits. When we look at such a circuit here, this is a load. It has a certain load, and when you believe in all these circuits, be aware that that load can be very complicated and measurement is very difficult. Anyway, so this is the generator that I used. Very simple square wave generator. We are now in the range from 1K, that is 1000 Hertz, up to 10,000 Hertz. And let's see what happens when we look at especially at the light and the frequency, of course. Voltage is now set to approximately 18 volts, 19 volts, also okay. And lift up the frequency, and you can hear the transformer beep. This is the waveform, needle pulses, 1.3 kilohertz. Let's go higher. 1.8 kilohertz. And now I will go very suddenly high, because my camera time is not unlimited. So, and now we reach, in a certain way, the frequency for which the transformer was made. Of course not complete, because we are only on 6.6 kilohertz, but the lamp lights up very fierce. So, we are not at the moment on the optimum resonance, that is around 16 kilohertz. And I can try it, but it could be that my Darlington burns out. But let's try it. More light. This is approximately, well, this is 13 kilohertz. Now we are really in the range. You can see that the waveform changes. That's very interesting. I cannot talk too much about it, because I don't have a very clear explanation for it. For me, it's simply a fact. 13 kilohertz, a lot of light. You can see it on the workbench. Well, try to get to 16 kilohertz, but I have to switch it back, because otherwise we get an enormous voltage jump, and that could damage the Darlington. Anyway, so let's go higher. So let's go to 16 kilohertz. Oh, we are 53 kilohertz. Well, that's a little bit too high. This doesn't work as nice as I had expected, but this is, say, 20 kilohertz. Not much difference between 13 kilohertz and 20 kilohertz, but I hope I have showed the principle of the circuit. You can find with this setup, I will show the schematic another time, you can find out the optimum resonance of a transformer. It could also be a transformer made for 300 Hertz, for 1 kilohertz, etc. etc. And that depends, of course, completely on the construction of the transformer itself. Say, the core can be made with ferrite. The core can be made with silicium steel, soft steel. The core can have a certain form. Can be an E-core, can be say a tube core, etc. etc. Also, this is a sea to drink, and I cannot go too deep. When you are interested, study electronics books. They can give you a lot of good information. So again, important things: disconnect this wire, send in here a frequency. It must be in the order of 5 volts. You can change the bias a little bit. I've not done that here, but that can also have very good effects on the maximum amount of light that the gas-filled tube strays out. Finally, let's look at the beautiful, beautiful light. It's real fun to see it work, to see how certain laws of electronics work, etc. etc. And thanks for watching.